Okay, number 3, the dreaded energy density problem. Well, not too dreaded. Remember, folks, check your marshmallow lab, check the burning Cheetos, burning nuts lab, and then think about the lab you do with the stove. It's all the same stuff. I would go back to the original lab because now you know more and you can probably understand more what you did the first time. Because we kind of held your hand through that, and the test asks you to do it without us holding your hand. So that can be dramatic sometimes. So make sure you practice until you can do it yourself. The logic behind all of this is that here is the can. This is a calorimeter. It absorbs the heat, energy of the fire. And we put a thermometer in there. And then we lit something on fire. In this particular case, we had a propane tank with a little stove on it, and we heated it, right? So we're adding thermal energy to the world. Really, we're heating up the world, and some of it's getting into the can. And we're trying to find how much of the thermal energy was released from here and captured in here. Okay? So this is the system. This is one part of the surroundings. We're going to see how much gets into here. And we're trying to find the energy percent yield. And what it's going to be basically is the kilojoules absorbed divided by the kilojoules given off. Okay? And the kilojoules absorbed is going to be basically the calorimetry problem. It's the Q is equal to MC delta T. So Q is equal to MC delta T. And when we're talking about absorbed, it's really kilojoules absorbed by water. And that might help you make sure that you get the right units. So here it is, folks. So Q is equal to MC delta T. The energy transferred by heat to the surroundings is going to be the mass of the water. You do you look at the thing, it's something like 64.53 grams of water. The specific heat of water, which is 4.186 joules per gram degrees Celsius. And then the change in temperature of the water is 37.45 degrees Celsius. You do the math, Q is equal to something like 10,116.1 joules. Also known as 10.1161 kilojoules. Okay, and I'm leaving the number long because at the end I'll trim it down. So that is the kilojoules absorbed. So maybe we can do that by water. All right? Okay. By who? By water. All right. So we've got that. Now we've got to figure out basically the kilojoules given off. So this is the absorbed by water. I'm going to go backwards again because it's kind of fun. So this is the kilojoules absorbed by water. Now let's figure out the kilojoules given off. Well, our stove is giving off energy, and in the marshmallow lab, or the nut lab, we measured the change in the mass, and then we looked at the package and said, oh, how many calories per gram? Oh, so we calculated how many calories should have been released. We don't have calories per gram, but we have in our equation, we have our delta H is equal to negative 2044.2 kilojoules per mole of propane, C3H8. So if I had a mole of it, it gives off that much thermal energy. Okay. So the question is do we have a mole? No, we have a tiny amount. So let's figure out, if we converted that to moles, couldn't we use this as a conversion factor to figure out the kilojoules? We could set up a ratio or do whatever we need to do. Because if we know this is how many kilojoules in 1 mole, if we have a large number, then we know this is going to be large. If it's a small number, we know it's going to be small, and it's proportional. So let's do the math. Looking at the math, the mass change, the change in mass of the C3H8 is something like 1.16 grams. So let's do it. I'm going to do one long conversion factor because I like it. So 1.16 grams of C3H8. Let's convert that to moles. C3H8. See how I set up the conversion factor when you start out with what you want? And I know that the conversion factor, the same units have to be done here. Grams C3H8. And what I want is up here, C3H8. Okay, here we go. So how many grams are in a mole of C3H8? Do the math. 3 carbons, 8 hydrogens. 44 44.098. That's ugly. Sorry about that. Ooh, getting uglier. Da, da, da. 44.098 grams of C3H8. Okay, all right. Do the math, and you end up with something like 0.0263 moles of C3H8. Let's use our conversion factor, now that we have moles, to go from moles to kilojoules. So here it is. All right. For every 1 mole of C3H8, we end up with 2044.2 kilojoules. KJ, not JK. And you do the math, 2,000, 20,000, wait, yeah, 2,044. This times this, and you end up with something like 53.8 kilojoules, because the moles cancel. All right. So there it is, kids. We converted from grams to moles. Why? Because we have a conversion factor that goes from moles to kilojoules. So we just wanted to get here just so we could use this conversion factor to go from moles to kilojoules. It's the energy mole. So this is kind of like energy versus the real world. But it's funny because it's the real world in number of molecules. And we can't really measure that in real life, but we can measure the mass of something. So we convert it into moles and then to energy. It's almost like we get from real to more abstract. But we're not done yet, kids. So we have the energy energy absorbed divided by the kilojoules of released. Oh look, we're all ready to go backwards. It's really great. So I'm going to say the energy absorbed divided by the energy released times 100. I'm kind of doing this like a Japanese manga. I'm going backwards, right to left. So the energy absorbed by the energy released. Look, we absorbed this much, but we should have absorbed that. That's like maximum. If all things were good in the world, we would have absorbed all of that. Although the laws of the universe, never mind, whatever. Something. This divided by this, it's like a fourth. So do the math, and you end up with 18.8%. So this is how much is absorbed or released. There you go. Hope that helps.